Hey, what is up everybody? This is Paul, and in this video I want to go through some of the basic matrix and vector operations you will encounter here in Numpy, which will hopefully give you guys a little bit of a head start when it comes to doing some of these data science things, because the way matrices and vectors work in Numpy is probably a little different than you're used to, especially if you're coming from a Matlab background. So I'm hoping this video will be helpful at just detailing these basic operations and helping you avoid some of the pitfalls that I ran into when I was taking 301. So I've created this Python notebook called Matrix Headache, and the first thing I'm going to do is import Numpy. Numpy. It helps if I spell it right. NP, and there we go. So the basic building block in Numpy is what's called an array. So basically is what I can do is create an array by just passing in a list or a tuple. So if I create an array of just this simple vector 1, 2, you can see that if I print it, and I print its shape, you will see it's just simply this row vector of 1 and 2, and its shape is 2, which is basically just saying it is a two element, one-dimensional array. Creating a matrix is very similar. We just say numpy.array, and we make it a list of lists. So the way that actually is probably the easiest to see is if you do it this way, and then you create your rows like this. 3, 4. And now if I print x, and I print x.shape, and let me comment these guys out, you can see x is a matrix 1, 2, 3, 4, and its dimensions are 2 by 2. Now this is where things get a little bit tricky, because if we take our matrix transpose that we're all familiar with, and we print x and we print x.t, you see we get 1, 2, 3, 4 and 1, 3, 4, 2, or 1, 3, 2, 4, which is exactly what we expect with this two-dimensional array. But if we try to take a, which is a row vector, and transpose it so we have a column vector, which those of us who are used to math and all these things, that's how we represent vectors, you'll notice that a actually doesn't transpose into a column vector. And the reason for that is because a's shape isn't two-dimensional, it's just one-dimensional. So the transpose doesn't really mean anything to a one-dimensional array. So the way we get around that is by actually adding a new axis to a. So if I say a equals, let's create a2, and the way I like to do this is saying a, and we just index it by adding a new axis to it. So notice this is the brackets for indexing, and all we're doing is we're basically saying a, and then by indexing it here, it's creating a new axis. So now if I compare a and a2, the shapes of both of these, a2.shape, you'll notice that a is a two-dimensional array, whereas a2 is actually a 1 by 2 array. A little bizarre. So now if I print a and I print a2, and then you can see they're pretty much the same, except a2 has an extra set of braces, which is representing this extra dimension that we have. And if we transpose both of these, you will see that a2 ends up getting transposed as a column vector, whereas a stays the same. So if you're working with vectors, I think it makes a lot more sense to, when you're trying to use a column vector, to use this new axis command to create it into an actual column vector. Now this will annoy you to no end, because when you're trying to do things that are even simple like matrix multiplication, things don't always behave the way you'd want it to if you don't have this new axis. For example, let's say we want to print numpy.matmul, so this is how we do matrix multiplication, and we want to multiply x by a. And we do numpy.matmul x by a2. So x by a actually works, even though it really shouldn't, because a is a column vector. So what happens when you're doing matmul in this case is it actually adds a new dimension to a, it does the matrix multiplication kind of the way you probably would expect, and then it deletes that extra dimension. So by deleting that extra dimension, you end up with a row vector, because that is just kind of the basic building block of NumPy. Whereas when it's two-dimensional, it's multiplying a 2 by 2 array by a 1 by 2 array, which isn't exactly, there's no way that's going to line up because the dimensions don't agree. So to make this line up, we need to transpose this row vector into a column vector, and there we get the result that we expect. Now, I actually don't think this first way of doing things is right, is the way you should be doing it, because you're taking a lot of liberties here with the way the dimensions work, how they're getting added and deleted. I would say first way is not desirable for two reasons. First of all, you're having these dimensions added and subtracted, which is one thing in and of itself. But the next thing is that notice how this result here is a row vector. That doesn't really make a whole lot of sense when you think about the way that this works. You're taking a 2 by 2 array, you're multiplying it by something that is really 1 by 2, and the result you're getting is something that is now also 1 row by 2 columns, or 1 by 2. Whereas this makes a lot of sense because you're taking a 2 by 2 matrix times a 2 by 1 vector, and you end up getting a 2 by 1 vector as your result. So this, I believe, is the correct, I would say this is the way you'd want to do it on the bottom, and this way is kind of, technically you'll get the right answer, but it doesn't really make a lot of sense. So my advice is when you're working with these row and column vectors, whenever you're doing matrix operations or matrix column vectors, transpose it into a 2D array and do the operations that way, rather than expecting it to work, I guess, the way you would want it to, because you're going to get all this weird unexpected behavior. So yeah, once again, anything whenever you index, you're going to run into these issues because of the nature of these arrays. Now there is an inherent Python data type that's built into NumPy called NumPy matrix, which forces everything to be sort of these two-dimensional arrays rather than one-dimensional, two-dimensional, or more and more. But that's going to be deprecated. So I would say use the array, but be mindful of the fact that you're going to be dealing with these elements that have different numbers of dimensions, rather than it being implicitly assumed that everything, like in Matlab, is kind of two-dimensional and you can transpose these column vectors the way you want it to. So to give another example here, just to really drive this point home, is we can print, so we know x's shape is 2 by 2. Now what if we were to print the first column of x? So this would be taking x, we would be taking all the rows, and we're going to take the 0th column. So the way indexing works is this first axis tells you the rows, and the second one tells you the columns. So in this case, I'm taking all the rows of x in the first column. So this would be 1 and 3. So if I print this, notice how this is a row vector of 1, 3. And if I print this dot shape, you can see it is indeed a 2-element vector that is, that is kind of a vector. It's not a 2 by 1 matrix. So once again, if we wanted to multiply x by its first column, the way we would have to do it is do np.matmul. We would have to say x, this, and we would have to add a numpy.newAxis and then transpose it to turn this from, this gets a row vector that is one-dimensional out of x from this column, transposes it on its side, so you get 1, 3, and then this transpose flips it back into a column vector the way we'd expect it to, and now we can actually multiply it by x. And doing that, 1 by 3 times this matrix, this gives you the result that you'd expect. Notice how if you didn't have the transpose, you would get an error because the dimensions don't add up. And if you don't have this, you end up getting a row vector, which is a little bit bizarre because this may not be exactly the behavior that you expect. And if you're trying to really keep track of your dimensions, which I would really encourage you to do so, this is like not the correct way to do it. So the next thing I want to talk a little bit about is the way axes work in NumPy, because this is also something that can be a little bit confusing. So let's say I do, I want to print NumPy the sum of elements of x. Let's say, so what I'm going to do is I'm going to say print b.sum x. Now by default, what this is going to do is sum together all the elements of x. So 1, 2, 3, and 4. But we can also, with this sum argument, also pass in an extra argument, which is the axis. So what happens if I say axis equals 0? Well, what it's going to do is it's going to go along the 0th axis, which is down the actual rows. So if you notice what's going on here, by saying axis is 0, this is going to add together 1 and 3 and give it a 4, and then it's going to add together 2 and 4 and give us a 6. And this is true about all the different operations. So there's sum, mean, all these other operations. Axis 0 is generally down the rows, kind of the way, or I guess, yeah, across the rows or down the columns. If I switch this to axis equals 1, you will notice now it performs this across each of the row, treating each of these elements as row vectors. So by doing this, we do 1 plus 2 is 3, and 3 plus 4 is 7. Now the reason this was built this way is you kind of have this interplay between statisticians and electrical engineers and math people, and with the statisticians really liking their matrices to be made of row vectors, and the electrical engineers and math people liking their things being made as column vectors. So this allows you to kind of bypass those weird issues where you're running into these things where whether you're trying to add together down or across, that's what this axis kind of allows you to do, is specify which dimension you're adding across. And then you have the computer science people who really don't know what they're doing. So that's kind of the way these axes work here. And when you're trying to do all these operations, you'll kind of see, for instance, if we try to do numpy.mean x axis equals 0, you'll see that this takes the average down the columns, and axis equals 1 takes the average across the rows. So in different situations, you may want it to be different ways. And that's where you can kind of run into these issues. Now, one thing you can do for this matrix multiplication that I think makes things a little bit easier is if you're here, rather than doing numpy.matmul, and then if you wanted to multiply this by something else, you need to do numpy.matmul again, it's easier to do this just simply as saying x at a2, just like this. So this at sign is the implicit matrix multiplication of x and our column vector a2, this is forcing it to be a column vector. So this kind of does the way we want to. We're basically taking 1, 2, and we're multiplying it across with this. Now you can also use this time signal, but what this is going to do is element-wise multiplication, which is not what you want, because this ends up getting broadcasted in bizarre ways. So let's say I take this transpose out. What ends up happening is it does 1 times 1 and 2 times 2 for this top row. Then it does 1 times 3, which is 3, and 2 times 4, which is 8. Now, there's a good chance this is not what you'd want it to do, because in theory, these dimensions don't even work out for element-wise multiplication. So Python tries to assume you know what you want by multiplying these elements and broadcasting this row across all the possible rows. But because it doesn't throw an error, if you're doing a complex, matrix operation, you're going to run into errors because it doesn't give you an error when you probably should expect it to. And this is why I would recommend really keeping track of your dimensions and where things are, kind of almost manually, because otherwise you can get these things where it doesn't throw you an error, you think it's doing what you expect it to do, and then later down the line it comes back and bites you in the ass because you were expecting it to give you the right value. And this is technically, when it comes to math, just incorrect. This should be undefined. There's no way to multiply a matrix by a row vector, but in its attempt to try to make things easier, I think it actually ends up being really confusing. So don't do that. The last thing I want to do is talk about, and this is related to this, the difference between inner and outer products. And this will come around a lot later in the course when it comes to, well, you've probably already seen it when it comes to the singular value decomposition, and I'll probably make a separate video about that. But let's see the way this works. An inner product, we know, is defined as taking a vector and transposing it and multiplying it by another vector. So when it comes to NumPy, the way we do it is we would take, if we wanted to take A's inner product with itself, we would do this as print, we'd say A2 dot. So maybe the best way to do this actually is first turn this into a column vector the way we'd expect it to, and then we do A2 transpose times A2. Notice how this is 1, 2 by 1, 2, so 1 times 1 is 1, plus 2 times 2 is 4, so 1 plus 4 is 5, and that's exactly what we expect. There are other methods in NumPy that will help you do this. For instance, you can say numpy dot, A2 and A2, But then you run into these issues where things don't quite line up. You can also do A and A, which tries to figure out the dimensions for you by taking this one and transposing it. But since these are row vectors, this is also, once again, completely incorrect, and it just is kind of confusing. So rather than memorizing it this way, I would say just work in, if you're trying to do these matrix operations the way it's notated and in the correct way, just turn it into a column vector first, and then everything works out the same way. So what this is doing as an inner product, this is taking a 2-row by 1-column matrix and it's multiplying it this way. So transposing this 2 by 1, and maybe I'll write this here. A2 is a 2 by 1 column vector. So by looking at this inner product, what's going on here is we're basically taking a 2 by 1 and transposing it. So we get a 1 by 2 vector times a 2 by 1 vector equals 1 by 1 scalar. And once again, what ends up happening is it gets into these double braces because the result is 1 by 1. So it's actually, oddly enough, a 1 by 1 array with 2 dimensions that's equal to the number that you expect. So you don't really get a scalar out of it, but you kind of do. And I think you can interpret this as a scalar and use it in computations the way you'd expect. Whereas with some of these other operations, that's kind of the way it works. Now, to do an outer product, it's basically the opposite. So whereas the inner product was, the way I like to think about this is the transpose and the inner product is inside this expression when you're working with column vectors. Whereas with an outer product, the actual transpose is on the outside like this. So if I do this, take a look what I get. I get 1, 2, 2, and 4. So what's going on here? Well, with an outer product, rather than a 1 by 2 vector by transposing this on the inside, we have a 2 by 1 column vector times a 1 by 2 row vector. Because this column vector is now being transposed and you have a row times a column. So if you think about what's going on, you're taking 1, 2, maybe it helps if I write this out. So you're getting 1, 2, and you are multiplying this by 1, 2. So first row, first column, you're getting first row of the first column times the first column of the first row, and you're getting 1 times 1 is 1. Now, in the first row, second column, you're taking the first row of the column vector and you're multiplying it by the second column of the row vector. So 1 times 2 is 2. Now, in this position, you are taking the second row of the column vector and the first row of the row vector, 2 times 1, and that's this 2. And then last but not least, in the second row, second column, you're taking the second row of the column vector and the second column of the row vector, and you're getting 2 times 2 is 4. So that's kind of what we mean when we talk about an outer product. Now, if you notice what's going on here with this outer product, what we end up getting is what's called a rank 1 matrix. Because just by definition, every single element of this, or maybe I should put it this way, every column vector of this matrix is a simple scalar multiplied by the original column that we have. So the other way to think about this is a 1 by 2 column vector, and in this first column of the matrix resulting, it's gotten by taking this 1 by 2 column vector and multiplying it by 1. So that's where you get 1, 2. And in the second column of this matrix, we're taking our column vector 1, 2 and multiplying it by 2. So that's where we get 2, 4 from. So that's another way to think about what's going on here. And just by nature of what's going on, by multiplying this, and we can extend this 3 and 4. In any case, all we're going to be getting in this matrix of when we do an outer product is simple linear combinations of the original column that we had. And that's just kind of another way to interpret what's going on with an inner product. So for instance, if instead of doing this, we multiplied it by numpy.array 1, 2, 3, 4. And the reason it doesn't like this is because once again, we have to add the new numpy.new axis. Now we can see we got 1, 2, this times 2, 2, 4, this times 3, 3, 6, 4, 8. So in any of these cases, all of the columns of this matrix are going to be simple linear combinations of the original column that we had. So the overall rank of this matrix is going to be only 1, because there's only one vector that's used to construct all the columns. And if you just choose one column, all the other columns of this matrix can be found by just some, linear combination or some multiplying factor times that original column. And that's what we mean when we get an outer product. We end up getting a rank 1 matrix because there's only technically one dimension that's present in the column space is kind of the way to think about it. Now we'll talk a little bit more about outer products when we look at the dyadic decomposition of the singular value decomposition, which I will talk a little bit about probably in another video. But for now, I hope this has been helpful understanding a little bit about inner and outer products and how Numpy kind of works with its indexing and why it would give you a headache. So let me know if you guys have any questions. Hopefully this was helpful, and I will see you guys later. All right, bye-bye.